Trusses. Yeah, there we go. Okay, trusses. We use a number where you're standing or sitting on top of a truss system. Okay? What is a truss system? It's a system of lightweight components that are hooked together to distribute forces. So there is a truss system under your feet. There is a truss system over your head. Your automobile frame is built on a truss system. Okay, so what we're going to do is just start off by discussing what is a truss system. So I'm just going to draw out a simple truss system like we would have under the floor here. Okay, so it's got two parallel components with some internal, oops, let's go all the way to the top. Cross members. Okay, we've got attachment points here and here. Kind of looks like the top of a Walmart store, right? You ever gone in Walmart and looked at it?
Yeah.
You got the trusses up there to support the roof. Okay, so we have attachments here and here. We typically mount those with a pin type structure so there's no movement. I have my bridge truss here. The bridge truss looks a lot like that, except it's got some extra components, okay? Why does it have extra components in this bridge truss that we're not having in this type of truss that we'd have in our roof? Because this bridge supports a lot more weight than what that roof is gonna support,
And
right?
bridge also needs to kind of move.
And the bridge does move, dealing with thermal expansion or linear expansion. Remember in physics, you talked about that. Changes in temperature cause metals to expand and contract. Well, these are combinations in bridges of more than one type of material, right? So they expand and contract at different rates, so you gotta figure that out. Okay, so if we label all of our parts based on their connection points, okay? Based on their connection points, what do we have? We have a bunch of different forces. So if we attach here a force of 5,000 pounds in this direction, and we hang here a force of 3,500 pounds, that's gonna be a massive truss that they're gonna have to design, because we're going to take into account all of the forces that exist on all of the members in that truss. Okay? There is going to be a force that exists between point A and point B, a force that exists between point B and point C, C and D, D and G, C and G, C and F, B and F, B and E, and A and E. Okay? And we're going to distribute these weights, these 3,500 pounds of weight and 35,000 pounds of force, we're going to distribute that amongst all of our connection points, okay? Because what is a truss? A truss is a structure made of lightweight materials, okay? In many cases, those materials can be considered to be somewhat flexible, okay? If we were to take the truss that's holding the floor up here apart, okay? Now, I do not remember exactly how they made that truss, but from the bottom view, it probably has a piece of angle iron and a piece of angle iron. Top has a piece of angle iron turned in the opposite directions. Probably 1 inch by 2 inch or 1.5 by 1.5. You can sit out here and flex that angle iron. Okay, you weld two of them together, you can still flex that angle line. Well, what they did to stiffen it was they put a webbing in between those two things. And when they did that, not only did it take the flex out this way, it took the flex out this way. Okay, so a few things we need to know. Trusses are made of what? Metal, steel, wire, what else are they made of? They're made of something called a two-force member. What is a two-force member? Something that has forces in two directions, right? Now we're gonna simplify those forces and describe those forces in terms of what?
X and Y.
X forces and Y forces, okay? Truss members are all pin connected members. What does that mean?
B.
What does a pin connected member mean?
Solid.
It's solid. There's no movement. There's no movement. It's a permanent attachment. Okay, there's no frictionless surface that you're sliding across. Why is that important?
Because if it can slide, the thing will just fall apart when you
If
go
it can slide, there's gonna be movement. We don't want movement, right? When you have movement, you have deterioration, right? You climb, if you're riding across the bridge and the bridge starts moving,
That's a problem.
you need to start considering other options, right? You know, whether that's spiritual or physical options, you need to start considering these, okay? What else do we know about bridges? Or trusses, I'm sorry. Truss members have negligible weight. We could say negligible mass compared to the entire structure. Now, have you ever watched a bridge being constructed? Whether it's something like the I-10 bridge or one up over a creek in Van Cleve or a bridge like this, what do they put first? The supports that go down into
Ground.
ground. Then what do they lay?
The cross.
They lay trusses of some form or fashion across, whether it's a pre-stressed concrete truss or a metal truss. What does that support?
The deck of the bridge.
The deck of the bridge. They don't bring the whole deck of the bridge in most of the time, right? They pour it in place, okay, unless it's a small bridge. So we've got these three things here about the trusses, okay? All loads on the truss occur at these pin connections of the members. And you're saying no. No, I've got my bridge here. There's weight here. There's force being exerted here if I park my truck right here, right? But remember, what is this? What is that section? What is this section right here? That is a two-force member, right?
Mm-hmm.
So if I'm exerting force there, where is that force distributed to? The ends. The ends. Okay? Now, have you ever, I know you may not do this, but do you ever watch videos on somebody that inspects a house or inspects a bridge or inspects a structure? So talking about if it's a pass or a fail thing. I like to watch the ones on house inspections. You know, you build a new house and they send in a house inspector.
He pushes the wall, it falls over.
He pushes the wall, or better yet, he goes up in the attic and you got the roof structure and you got the walls. But what do you notice that I leave in there? I've got space. Okay, I've got space. So the first big load that's put on the roof, if there's a space here and a space here, there's no connector. What are we gonna have occur? Movement. When we have movement that occurs, what's that gonna cause? Possibly some type of catastrophic failure. Okay? And we don't wanna have a catastrophic failure unless we're intending to have a catastrophic failure, right? Like if we're gonna blow up the house and let it crash, what do? We go cut some holes somewhere for that to occur, right? Okay, so you see that when you're looking at videos on this. So here we have, our ultimate goal is no movement. So it's stationary. So if there's no movement, then anytime we have a rotation, how much rotation do we have? None. So the sum of our moments would be equal to what? 0. Okay? So the sum of our forces in the x and the y direction would both be equal to 0. Right? That's our goal here. Okay? That's our goal. Is to have our sum of our forces in the x and y direction equal to 0 and the sum of the moments equal to 0. Okay? So let's look at a truss. Now we can solve for the components of a truss 2 different ways. Okay, today we're going to look at it in terms of the method of the joints that make up the truss. That's one way. Okay, on Wednesday we're going to look at a different way. That's totally up to you which method or which direction that you proceed in determining these forces. Okay, so let's take a simple truss. Okay. Okay, we've got a truss like this, and on this truss we have some additional forces. Okay, we have placed some additional forces.
Is that 9 or 4?
4.
Okay.
Okay. Within our truss, we're just going to put. I'm going to put the external forces that we have applied in red. We have a 5 kilonewton force here. Okay, and we have an 8 kilonewton force there. So we've got 5,000 newtons and 8,000 newtons. So we've got about, what, 10 pounds and 8 pounds, right? You ever take a little bit? 10 pounds and 4 pounds, sorry. Okay? Now, how many members make up this truss? How many members make up this truss?
Looks like 4 members.
How many? What is a member? Something that connects 2 points, right? Now remember, all points are what type of connections? Pin connections. So there's a pin here, a pin here, a pin here, and a pin here. So how many members do we have? 5, right? Do you see 5? You got this one, and this one, the 3 easy ones, right? And then you have this one, and then you have that one right there. Okay, so you've got 5 members. So how many forces will you have? You will have the 5 forces that are instant on those members, right?
Mm-hmm.
Plus what?
The moments.
Any other forces that you have there. Okay, so let's take our truss. What's an application of a truss that looks like this? Have you ever, do you think about things in those terms? Can you find an application of something like this?
Might have some. When you put up a piece of 2x4 to help hold plywood up on a window during a hurricane. Like,
Well, yeah, but you usually don't put 2 pieces of plywood. How about something else? How about a wheel chock? Do you know what a wheel chock is?
oh yeah. Yeah, it's like
Keeps you from rolling. It's a triangle. Keeps you from rolling. When do you use a wheel chock?
camper, trailer.
Well, I was saying when you change a flat tire, right? Okay. We use it a lot more when we change a flat tire to keep the car from rolling. Why? You don't want the car to roll while it's up on the jack, right? Because then it's a lot more trouble to get the jack back under it, right? So application here would be something like a wheel chock. Now, Why is it made like this? Just for more support, okay? So, what are our members that make this up? There is member AB, there is member AB, there's member BC, there's member BD, and there's member CD. We've got 5 components, so we've got 5 forces, okay? We've got in red our external forces, and in black we have our internal forces, okay? Now, you're thinking, oh, Stringfellow said the sum of the moments, sum of the forces in the x and the y direction are going to be equal to 0. So that means the sum of all these internal forces is going to be equal to these external forces. No, no, it's not, okay? Because I could keep adding force to it until it moves, right? But I'm not. I'm looking at this particular situation here, okay? So we want to find the forces in each of these members. We've got 5 members. We want to find the forces in each of these 5 members, okay? So how do we approach that? Well, there's some steps that we can follow. There's a 3 or 5 step system, okay? So step 1, which is, I think, the easiest step to take, okay? So step 1 is we find the equilibrium of the system. Some people may call this the global equilibrium. Why are we finding the global equilibrium? Because what do we have? We have a system, and it's got external and internal forces. So let's look at our system. So we mount it here and we mount it here. It's in contact with the ground if we're using it as a wheel check at those 2 points, okay? So with that, do we have any other forces that are exerted?
Force normal at A and force normal at C.
Okay, we could say we have a force normal, but, okay, so we've got 2 forces like that, an AX and an AY, right? What direction are they in?
Well, if that one's pulling that way.
If that one's pulling that way, that one's gotta be going that way for AX, right?
And if the one at B is pushing down, AY's got to push up.
Push up. Except, where is AY pushing down at?
That's
B.
positive.
Where is it on the ground at? C. Okay? Why does that make a difference? Why does that make a difference? Because we're looking at the sum of the forces in the x direction equal to 0, the sum of the forces in the y direction equal to 0, and the sum of the moments equal to 0. If this was out here, we're obviously going to have a CY force pushing up, right? Because it's out there. What are we going to have here for an AY force? If CY is pushing up, then AY is going to have to push down. Because those are our 2 points where they're matching with the ground, where those pin connectors attach. Okay? Now, for all of these, we're looking for these, and we also need to know are the members in compression or tension. How can you describe a member being in compression or in tension?
Compression is being pushed together.
Progression is
Tension is
being
being
pulled apart. So if we're looking at point F, which is not on there, if the direction of our force is to point F, What is that described as? We're compressing point F. If it's away from point F, then that would be tension, right? Okay, so our first step is to do that. Our second step is to pick a point. Okay, just pick a point. What's a point? A connection. A, B, C, D in this case. Okay, we're gonna pick a point and then we're going to draw a free body diagram. We're gonna pick a point and draw a free body diagram. Okay? Step 3, we're gonna solve the free body diagram for our unknowns. Okay? Now I'm gonna put a little caveat here with step 2. Okay? We wanna be careful which points we start with, because we do not want to pick a point and draw a free body diagram that has more than 2 unknowns. If we have more than 2 unknowns, we cannot solve for the unknowns. Okay? Does that make sense? You got more than 2, you can't solve for. So we've got step 1, step 2, and step 3. Now, we do that for each point. Or we do it until we find AD, AB, BC, BD, and CD. In this case, we may not have to do all 5 points, all 4 points. We may just have to do 2, we may have to do 3. We got a bridge like this, what are we gonna have to do? A bunch of them, okay? But they're all free body diagrams and we're just solving for the points. So let's start at point A, or joint A. So if we have joint A, okay, take a second and draw the free body diagram at joint A. Just right here. All we want is right here.
I think I got it.
Okay, so at A we have AX, right? We have AY. What else do we have?
4 foot away, we have 5 kilonewtons.
We have AD, right? What else do we have? And we have AB. Now, how many forces do we have in the X direction?
We have 2.
How many forces? Okay, we do have forces, 2 forces. What are they?
5 kilonewtons at 4 foot away.
Okay, just tell me what they are, not where they are.
Force.
What are
Your AX and your 5 kilonewtons.
Okay, that's it. Now guess what? They're acting on the same line of action, right? So AX has to be equal to 5 kilonewtons. Well, at point A, this is 5 kilonewtons. What's AB?
5 kilonewtons.
That's 5 kilonewtons. Okay? By definition there. So AB is 5 kilonewtons. Now, is it a compressive force or a tensile force?
Well, it is.
What?
Tensile.
Tensile. We're pulling, right? We're pulling. Okay, so it's the tensile force. Now, can we solve for anything else there?
Maybe, okay. So we know AD, AY, and 8 kilonewtons are all on the same line of axis.
So we know this, right? That the sum of the forces in the y direction are equal to what? 0. Do we agree with that? Okay, so what are they? Negative AY minus 8 kilonewtons plus CY, right?
CY or, oh, over there.
CY, okay? Can we solve that?
Can't really. 8 kilonewtons is equal to CY minus AY. As far as we can get.
Or, yes, CY minus AY is equal to 8 kilonewtons. Can we do anything else? Can we do anything else?
I don't know.
Well, how about we go back to our global equilibrium? For our global equilibrium, can we do anything with our global equilibrium?
CY minus AY plus 8 is equal to 0. That's your global.
We could look at point C.
Go back to your global equilibrium. In our global equilibrium, some of the forces in the x direction have to be equal to 0. Some of the forces in the y direction have to be equal to 0. The sum of the moments must be equal to 0. Okay, can we find it with respect to the moments?
Can't see really why not.
Do we have any moments? We have moments around point A. How do I know we have moments around point A?
There's a force and there's
Because there's forces at a distance from point A, right? So couldn't we say, if we're looking at it in this direction, the moment of point A is 0 is equal to what? A negative 5, right? Okay. What about this one? Plus a negative 8 times 3 plus a positive 4 times CY, right? So that's 20, that's 24. So 44 kilonewton feet divided by 4 is equal to CY. So what's CY equal to?
11 kilonewton.
11 kilonewtons is equal to CY. Can we use that anywhere here?
Can use it in your force Y thing.
So the sum of the forces of y equal to 0 is equal to a negative AY minus 8 kilonewtons plus 11 kilonewtons. So what's AY equal to?
That's negative AY. So 3. Negative 3 is equal to negative AY. Negative 1 by negative 1. AY is equal to 3 kilonewton.
Is it positive or negative?
Well, if you go by signs, it's going to be.
That's 3, and that's negative. So it's negative 3. So what direction is it in?
Down.
Down. So what's AY equal to? 3 kilonewtons. So what does that make AD equal to?
AD is going to be your C is going to be equal to
3 kilonewtons. What is it going to be? Tensile or compressor?
done.
moving away, right? It's stencil. Okay? So, we've got all four members defined at point A, right? All four forces. Okay? So, let's move to the next point, right? The one thing I hate about this is you can't move up, so I'm gonna add a point to it. So we've got AD, AB, we need BC, BD, and CD. Okay, so let's look at point B. Point B.
Okay, about B is starting to have.
Draw a free body diagram at point B. Take a second and draw a free body diagram at point B. Or at joint B.
B. So there's gonna be BC, and then that angled one is ED with a 5 kilonewton up here. BC, there's going to be.
Does it look like that? Center point's B. Okay, what do we know? How can we label this? Well, this is what? BC. This is AB, right?
Bond's 8 kilonewtons.
This is a kilonewtons, and what is this one? BD. Okay? BD. Do we know anything? How many unknowns do we have right there now?
Okay, we already know.
We've got 3. We've got to have 2. Is there anything we can
We
label?
know AB is 5 kilonewtons in tension.
So,
We can knock that off. from what we
okay, so
previously
this
know.
is 5. So now we have what? 2 unknowns, right? Now, what degree, what type triangle do we have? We know this is what? 3. This one here was 4, and this one is 5, right? What kind of triangle is that? It's that wonderful triangle that everybody likes, right? That 3, 4, 5 triangle that we, make sure everything's square. From that, we can look and define the angles, right? So if this angle here is 90 degrees, what's this angle right here?
And that is.
Or what's this angle here?
Top one's 30, goes
Not 30, not exactly 30. It's 30 something. What is it?
35?
A little bit better than 35. Maybe about 36? 33? 5,436.2? Okay, how can I find this angle? Or how can I find this angle? If I'm looking for this angle, theta would be equal to the what?
Tangent, -1, 4/3.
Okay, the inverse tangent of 4/3. Okay? If I'm looking for the top one, what would it be?
Inverse tangent 3/4.
Okay? So couldn't I find that it's around 57 degrees? 53 degrees, I'm sorry, it's around 53 degrees.
We'll do 3.13.
So that makes the top one equal to what? 36.87. Why?
90.
90 plus 90 has to be 180, right? Okay, so what else do I know? So what is this gonna be equal to? What can I do? What can I do? How can I solve this? I've got two unknowns, BC and BD. What can I do? Could I not say the sum of my forces in the x direction equals 0? The sum of my forces in the y direction equals 0. What are my sum of my forces in the x direction?
So, okay, so AB and BC.
I'm gonna say a negative AB, right? Just pulling in that direction. Plus BC plus what?
5 going positive because that's at D.
5? Where are you getting 5 from?
Plus BD times a.
Plus cosine. A or B.
Plus BD cosine theta. Right? The x component. What's the y component? Sine theta, okay? So what's the sum of the forces in the y direction?
8 kilonewtons, which is negative because it's down. Kilonewtons plus.
Wouldn't BD be negative in the x direction?
Y'all told me.
So that's newtons, and then plus because it's going up. BD sine.
Right? Can we solve that?
Yeah.
We can solve for BD here, right?
Yeah.
And plug in here, since this is 5 kilonewtons for AB. And we can solve and find BC and BD. Okay? So what is BD?
Sine 53.13 is about
10?
0.79.
Just 10?
10.0000.
10. Okay? Is that compressive or tensile? Okay? So now we've got BD. What is BC?
Okay, it's equal to BC minus 10.00 kilonewton cos 53.13.
11.
11. Okay, is it tensile or compressive? What direction is the arrow? It's pointing away from the point, so it's gonna be tensile. And here is a good time to mention this one important statement. All members of a truss cannot be tensile. All members of a truss cannot be compressive. You've got to have a combination of tensile and compressive forces. Why?
So if it's all pushing together.
If they were all tensile, what would we be doing? You know what that bridge be doing the whole time out there? It'd be rotating, right? We don't want it rotating. We want some pushing up and some pushing down. Okay? So, I agree so far. We've got 4 tensile forces. So the force that we're fixing to look at, that last one, has to be compressive. Now, a little bit of other useful information. If you know the 4th or the 5th or the 247th force is compressive and all the others are tensile, you cannot just take and sum your tensile forces and set them equal to your other one. Okay? So like here, we've got 10 and 11, right? Both tensile forces. What were the first two we had? 5 and 3, right? So 5 and 3 is 8, plus 10 and 11 is 21, so that's 29. So I'm through. The compressive forces must be equal to 29. No, you can't do that. Okay? You can't do that. So how can we find this? We've got, what are we're looking for? AB, BC, AD, BD, and what's left? Force-wise?
CD.
CD, okay? So CD must have to include point C and point D, right? So let's look at point D. Draw your free body diagram for point D.
D's there, we've got. Let's go 5 down and come off that way.
If you want to do it from point C, draw it from point C.
Alright, got it.
What would it look like at point D?
AD is going like that, BD is going like that,
Okay. AD would be straight down, right?
straight down, BD at a little bit of an angle from the point, and CD is the furthest one out. And then there's a 5 kilonewton force going across like that, yeah. I'm bad at explaining things.
Okay, how about point C? How about point C, or joint C? We would have, if this is joint C, we would have this, what's going back that way? BC, right?
Mhm.
What else would we have?
C,
CY, going that way, right? What else would we have?
C,
CD, and it's kind of at this. Now, what angle does CD make with BC? Look back at your original diagram. The rise is 4 and the run is 4, so what's the angle? 45 degrees. Okay, which diagram, we know CY is equal to what? What did we say CY was equal to a while ago?
CY is equal to yellow.
What did we say BC was equal to?
11, 20.
Can we solve that? Which, that one looks easier than that other one, right? Okay, can we do that?
Yeah.
So, what is it? 11 kilonewtons plus a negative CD times the cosine of 45 is equal to 0. 11 kilonewtons plus
Sine.
sine of CD of 45 times CD is equal to 0.
Okay.
Right? Can we solve that? So CD is equal to what? Kilonewtons divided by what? So what's CD equal to?
$15.56.
And we already decided that since we have 4 tensile forces and we're looking for 5 forces, that this one must be compressive. Can we double check that? For it to be compressive, what direction does it have to be equal to? What direction does it have to be heading?
Towards up.
towards point C. Towards point C. Right? Is it heading towards point C? We drew it backwards there, but it's still heading towards point C, right? Okay, so we've got our 5 forces, okay? So that is one method to break a truss down into the members that make it up. That is the method of what? Joints, okay? So on Wednesday, we'll do the method of components, okay? So we'll cover off there today. I hope y'all can swim to your car.